All right, this is Chapter 5 from your Essentials of Radiographic Physics and Imaging book, which begins on page 53. And as a technologist, having an understanding of the X-ray tube and every component contained within it, how it functions, how the settings on the control panel affect the function, is vital to us understanding not only how it operates, but how to protect patients from unnecessary radiation dose, as well as protecting the tube from damage as we use it daily. This is a picture here of an actual X-ray tube. This is called a diode, meaning that it has two electrodes. It has a positive electrode, which is the anode, which is right here, and it has a negative component, which is the cathode, which is right here. And actually the portion that we utilize is right here in the focusing cup, and the anode right here is the positive side. So we have the negative cathode, the positive anode. When you have two electrodes with opposite charges, this is called a diode, meaning that it only allows electron flow in one direction. When we start off, before we get to the actual X-ray tube, we have the tube housing. And this is a picture here that you can see of the tube. This is the X-ray tube that we were just looking at. This is the anode, this is the cathode, and this right here was the Coolidge tube that both electrodes were contained in. But it doesn't just sit out over the patient open like that. It's actually contained within a protective housing. So the housing gives it a mechanical support. The housing is actually lead lined. It has an oil bath, meaning that this entire thing is filled with oil to help dissipate some of the heat that's created. It can potentially have cooling fans in there. It has electrical insulation so that there's no risk of electrocution to the radiographer or the patient like there was when X-rays were first discovered. There are large cables that come out of the top of this. So this is on the anode side, so this would connect to the positive side of the generator. And this is on the cathode side, so this would connect to the negative side of the generator. And this housing also helps to absorb any photons, which are these blue lines here represented by that sine wave. The housing helps to protect the patient and anyone else in the room from these photons escaping. And these photons are considered leakage radiation. Okay. When they start talking about X-ray production, it is a very inefficient process. So that 99% of what is created is actually heat, and only 1% is actual X-ray production. So a very inefficient process as a whole. And that 99% that is turned into heat has to be dissipated in some way, and that's where that oil bath comes into play. Okay, now this housing here, typically this protects the X-ray tube itself. An average tube life, assuming that it's taken care of well, that you do all the preventative maintenance, is probably about 5 to 7 years. All right. Now, notice I have this labeled as leakage radiation, which means that ideally you want the radiation that we create to come out here, which is the window of the unit. And notice it says here that this is the useful beam. This is the portion that is directed down towards the patient. It's called the primary beam. So what comes out of here is directed towards the patient. Anything else that escapes at an area other than the window of the X-ray tube is considered leakage radiation. And there is a certain amount of leakage radiation that is acceptable. You are allowed less than 100 millirentgen per hour at a distance of 1 meter. That is the amount of leakage radiation that is considered acceptable. So 100 millirentgen per hour at a distance of 1 meter. And if you were to convert that into the SI units, it would be 0.0258 millicoulombs per kilogram per hour at a distance of 1 meter, which is a little more or less than 3 feet. So coulombs kilogram is the SI unit, and millirankins would be your traditional or British unit. So there is a certain amount of leakage that is acceptable, but it cannot exceed that, and the state actually comes in and tests that amount of leakage radiation, and if it exceeds that number, then the state would force you to shut down. When we look at the housing and its construction, there are two things that they caution us about. With an extended on time, meaning that the x-ray tubes are typically in constant use. You're constantly receiving patients from the emergency room, constantly getting patients in there to be imaged, whether it's an outpatient or inpatient or emergency room trauma patients. So with the extended on time, the housing can actually get hot. A lot of times this will happen with the fluoro unit, but with the fluoroscopic unit, the tube is actually located under the table. The radiographic tube that we usually use to take our images is above the table, but when we do fluoro, the tube is below the table. So when it's below the table, it limits how much interaction there can actually be by people touching it, because it's protected by the table. So typically that's why the fluoro tube is underneath, is so that it protects the radiologist, the radiographer, and the patient. But also, with extended use, the tube housing that is above the table can also get hot. So you have to make sure that no one is actually touching that, the patient included. They also warn us that the cables that come out of the tube, that come out up here, that we're not to use those like handles, meaning that you should never pull on the cables that come out of there. It'd be kind of like when you have something plugged into a wall, you typically aren't supposed to yank on the cord to unplug it. You're supposed to walk over and actually touch the portion of the plug that you're allowed to touch to disconnect it from the, you're not supposed to really yank on that. When we look at the actual x-ray tube, it is a general purpose tube, meaning that typically this can accommodate most all the exams that we are required to perform. Typically a general x-ray tube is a vacuum, meaning there is no air inside of this. So this is a complete vacuum. All the air is removed from this. It has an anode, which is the positive side. Okay, so this whole portion is the anode. And it has a cathode, which is the negative side of the tube. So the cathode is one electrode, it's the negative electrode, and the anode is the positive electrode. Typically, it also has an induction motor, and that induction motor is made up of the rotor and the stators. And the purpose of that is to actually spin this anode to help dissipate some of the heat that gets created. All right, so you have an anode, which is positive, cathode, which is negative, and the induction motor, and they are all encased in a glass or metal envelope or metal enclosure. All right, so this one happens to be a glass enclosure, but they do make them out of metal as well. They reference that the anode typically has an anode target and the induction motor. So you have the anode target and the induction motor, which is the stator and the rotors. And typically the rotor is inside the glass envelope, but the stators are actually outside the glass envelope. So the rotor portion of the induction motor is inside. You can see how the glass comes through like this, both sides. So the rotor's inside, the stators are actually outside the glass envelope. The cathode on this side has what's called the filament or filaments and a focusing cup. Okay, this is where the electrical supply is placed. It comes in from the top and it supplies electricity to the negative side of the tube or the cathode. And it's typically composed of the filament and the focusing cup in here. And that makes up the cathode portion. When we look at the purpose of the enclosure is to maintain the vacuum that is within the tube, because when we produce X-rays, there's an interaction between electrons that come from the cathode and the anode target. And if there was any air present in that tube, the electrons would actually contribute, the electrons that are found in the air would contribute to the electron stream, and it could cause arcing, which could damage the tube. And if the glass envelope was to arc or create an arc, because it's a vacuum, that tube would actually implode. It wouldn't explode, but it would implode and cause damage. Okay? Typically, the glass envelope is made of, so this glass is made of what is called borosilicate glass, borosilicate, borosilicate glass, which is actually a term for Pyrex, Pyrex, which we use a lot of time in baking glassware. So it's made of borosilicate glass because it's very heat resistant. What happens though with these glass tubes is as it gets older, you end up with some vaporized tungsten from the filament can actually deposit on the inside of the glass, which is called the sun tanning effect, or makes a gassy tube. And that can lead to arcing and damage of the tube, because then you end up with little pieces of metal down here, pieces of the filament down here, and the electrons actually come from the cathode down to the metal, and they kind of spark. And if that spark creates an arc, then this whole thing would actually implode. So that is a problem with the glass enclosures. But the metal enclosures, they tell us, the metal enclosure provides a constant electric potential between the electron stream from the cathode and the enclosure, so you don't have the problem that you have with the glass tubes and the arcing. So metal tubes actually last a bit longer than a glass tube. And I believe the only difference is truly that the metal enclosures are a little bit more expensive than the glass enclosures. Okay, typically both of the enclosures, either glass or metal, have a specially designed target window for the desired point of X-rays to be produced. So when we look at this, or if we go back to that initial picture, they actually have a window where we would like the X-rays to come out. This is where we want our primary beam to be. Okay, so this window is actually made so that that area of glass is a little bit thinner so that the X-rays can actually get out. So that there's not as much absorption of the radiation in this area. The thinned out portion of the window actually allows the photons to exit, which is what we want. That's pretty much where we would like the X-rays to come out so that they're directed down towards the patient. So both metal and glass enclosures have that specially designed target window. So it's an area that's thinner. Now, let's look in depth at the anode. So we said the anode is the positive electrode of the tube, okay? And the purpose of the anode is to provide a target for the electrons to interact with. This is actually on the anode is the precise area where the X-ray photons are produced. So what happens is you get electrons from the cathode and they stream over to the anode, okay, and they smash into an area on the anode called the focal spot. And when they smash into that focal spot on the anode, all of that kinetic energy of those electrons is actually converted into electromagnetic energy in the form of radiation. Now, the electrons that don't become radiation, we said 1% becomes radiation, 99% actually becomes heat. But some of those electrons, when the exposure is over, does it make sense that you have to go back to a complete vacuum again? So you can't have any leftover electrons in this tube. So some will smash into the anode and actually create radiation, but some of them will strike the anode, not create radiation, but they have to leave the tube at the end of the exposure so that it remains evacuated. So what they end up doing is becoming part of the electric or the electricity that flows out of the anode. So when those electrons interact, they can either become radiation, which happens a small amount of the time. They can actually become heat, which happens 99% of the time, or the electrons can continue through the circuitry as part of electricity. All right. Now, when we get to talking about the cathode, I'll tell you how many things we're talking about. Because when I say 99% and 1%, it sounds really, really inefficient. But you have to assign numbers to that for it to truly make sense. So when we get to the discussion of the cathode, when we get to the discussion of the cathode, we'll actually give you numbers to assign to that so that you can see what kind of numbers of electrons we're actually talking about. Now, we have two types of anodes. We have this, which is a picture of a stationary anode, and we also have what's called a rotating anode. And this is way more common in our general purpose tubes. This is typically what we use. This is the one that has the induction motor, the rotor and the stators, which actually turn this to help dissipate the heat. But some of the older portable units and most dental units actually have what's called a stationary anode. And this is the area where the electrons would strike, this little square right in here. So typically a station anode has a tungsten button right here embedded in a copper rod. This does not move, but the problem is, the downside to this is because it does not move, the heat is not dissipated, so it actually damages the anode much quicker than when we use the rotating anodes that we typically use in a general purpose tube. Okay, so the rotating anode is typically what is in use today. And what you have is a rotating disc made of multiple materials. The bulk of the anode, the face of the anode, is made of tungsten, which is number 74. There's also some rhenium in there, which is number 75. But at the base, you have what's called molybdenum. You have a core material that's molybdenum, and that is number 42. So you take the molybdenum core and then you coat it with tungsten and a little bit of rhenium on there. Okay, so it's about, if I remember correctly, it is approximately, let me see if it ends up saying in here. Tungsten, rhenium. I want to say it typically has about 90% tungsten and possibly 10% rhenium in that. And the purpose is to spread out the heat that's produced during X-ray production over a larger surface area. So I'm going to try and draw this and show you what I mean. So let's say we have the anode. Okay, and in that anode, you're going to strike this spot right here repeatedly. So when you're doing that, if this didn't move, you would keep striking this same area over and over and over and over and over and over and over, just like we did with the stationary anode. And what would happen? You would start to wear out this area on the actual anode. But if this spins, then what happens is if you continue, we'll change color, if you continue to hit right here in this area, but it's spinning, then you're actually striking multiple areas because this is spinning around and round. So you're actually helping dissipate the heat over a larger area, and you spread that out as this continues to turn. So much better for what we do in X-ray, because if we're constantly taking images and we're spreading this out over a greater area, then that's more beneficial. So when you have that anode, okay, what we're actually talking about is the area that you strike right here is called the focal spot. Focal spot. That is the exact area where X-rays are created. Okay, but what happens is that when you strike that and it's moving and you spread it out like this, you actually create what's called a focal track. So focal track, and that helps spread out that heat. It dissipates the heat. Okay, so a rotating anode is much better because it spreads that heat out over a greater area and it increases the tube life. Now, as far as the materials that make up the anode, we have copper as part of the shaft because it has excellent thermal and electrical conductive properties. So that's good to dissipate the heat, and it helps attract the electrons that are coming across the tube. We said that we use molybdenum as the base and the core because it has a very low thermal conductivity, which allows the heat into the rotor bearings, so it minimizes the heat damage, and it's a light alloy, which makes it easy to rotate the anode. Okay, so molybdenum is our base and our core. Molybdenum is number 42. Copper is number 29. Let me double check before I tell you wrong information. Copper is number 29, correct. So we have copper, molybdenum, and then we have tungsten because it has a very high melting point. Okay, the melting point of tungsten is 3,400 degrees Celsius, 6,152 degrees Fahrenheit. So extremely high melting point. But it also has a high atomic number, which is number 74, which makes it really good for X-ray production. And like I said, we also add rhenium to this, which increases the thermal capacity and the strength. And rhenium is number 75. So when you add two of those metals together, you're actually making an alloy, which makes it much stronger and much more heat resistant. You rotate the anode that's on that positive side of the tube using an induction motor. And remember, we said the induction motor is composed of two parts. It has a rotor and a stator. Okay, so the two parts of the actual induction motor are the stators and the rotor. And remember that the stators are outside the glass envelope and the rotor is actually inside the glass envelope. So it says the stator is made up of electromagnets. They're actually fixed electromagnets that surround the rotor. And the stator is outside the tube enclosure, outside the evacuated glass envelope. The rotor has an iron core surrounded by coils, but the rotor is found inside the glass or metal envelope. So the rotors and the stators do not touch, nor does the rotor have any electricity supplied to it. Okay, so there's no electricity supplied to the rotor, and the rotors and the stators do not touch because one is inside the glass envelope, which is the rotor, and the stators are actually outside the glass envelope. Now, when we have the induction motor, it's actually operated through what is called mutual induction. So the stators actually get energized and create an electric current in the rotor that creates a magnetic field. And that magnetic field is actually what turns the rotor. Okay, so that process where the copper gets supplied with electricity, that copper gets electrified, and those fixed electromagnets, when it's supplied with electricity, it becomes a magnet. And when it's a magnet, it turns the rotor, which turns the anode. When the supply is stopped, it no longer is a magnet. This operates the same exact way that the locks on the X-ray tube work. When you depress the lock, it releases the magnet and allows you to move the tube. And then when you let the lock go, it actually clamps down and becomes a magnet again. So the stators act in the same way. When you supply them with electricity, they actually become magnetized or turn. They have that electricity, so it becomes a magnet, and it spins the rotor, which in turn spins the anode. So when I'm talking about that, when we look back at this picture back here, so these are supplied with electricity, the stators get supplied with electricity, and they become a magnet, which causes this to spin. And when this spins, since this is attached to it, it causes the anode to spin as well. So when you're looking at it, you're looking at it face on, and this is the anode, so it's actually going to spin, and it spins really fast. It spins at approximately 3,400 degrees or 3,400 revolutions per minute. Okay, spins at 3,400 RPM. So the induction motor allows for the rotation of the anode in the vacuum without having the motor actually in the vacuum. And a general purpose tube is capable of 3,400 RPMs. And if it was a specialty tube, it can go up to 10,000 RPMs. So our tubes that we typically use are 3,400 revolutions per minute. All right, now the anode that is located in the glass envelope actually has an angle to it. And when we angle the face of the anode, it allows to use what's called the line focus principle. Okay, and the angle that they're talking about is actually right here. This area right here is angled. Okay, if we go back and look at the X-ray tube, go back and look at the X-ray tube, they're talking about this right here. Okay, so that angle, when we look at that a little bit closer, because we angle this anode, it allows us to create a larger focal spot, meaning that the area that actually gets bombarded with the electrons is greater. So these electrons are coming across and they're interacting with this entire area of the anode. But because it's angled, when they are released, they're coming out at a much smaller area than what they were sent over in. Let me erase that and start over. So what happens? Okay, you have got the area that you're actually interacting with goes from here to here. Okay, you're interacting with that entire area. But when it comes out, I'll change colors for you. When it comes off of it, notice that it's coming off in this small area right here. Let me change the color to something you can see. All right, so it interacts with that whole area in red, but when it exits the tube, See how this area is much thinner from side to side? This is much thinner, sorry, than this whole thing right here. So because we angle the target, it allows the X-rays to come out of the tube in a more confined area. And what that creates is the effective focal spot. So the effective focal spot is always smaller than the actual focal spot. And what that allows for is resolution. Okay, that allows us to have the most amount of resolution on our image. So let me go back to that again. The line focus principle basically says that if you angle the face of the anode, you can have a large actual focal spot size, like a large area that can get bombarded with the electrons, and it will still create a small effective focal spot, which gives us much better resolution. All right, so the only purpose, like this focal spot, what we're talking about right here, this focal spot is actually the source of photons, meaning when the electron comes across and smashes with the kinetic energy into here, it releases a photon of energy. So this area right here is always our source of X-rays. The focal spot is the source of X-rays. And if you angle the anode, it allows for much better resolution on your image. Okay? Typically when we have the target angle, usually they vary anywhere from 7 to 18 degrees for a general purpose tube, but the most common target angle is 12 degrees, meaning for a general purpose tube, typically it's going to be a 12-degree target angle. Right? And what happens is when you angle that, the smaller the angle, the smaller the effective focal spot. So when you have a smaller angle, actually here, I can show you that right now. When we have a smaller angle, okay, so this is only a 10-degree target angle. This is a 15-degree target angle. And look at the width of the blue. So when we have a 10-degree target angle, much more narrow from side to side versus the 15-degree. So when you have a 12-degree target angle, you're still getting a relatively small effective focal spot size, which means that we're getting much better resolution for our image. Okay, so the smaller the anode angle, the smaller the effective focal spot will be, even though you have a large area of interaction right here. So you can send a ton of electrons across to smash. Let's start over. Send a ton of electrons over to smash in this whole area, but the way they're coming out is much more confined, which gives us much better resolution. Now, when I'm talking about how much is actually coming across and interacting with that, all right, when we look at we're also going to look at the anode heel effect. But when we talk about this, all right, this is all radiation. Notice this is all in wave form right here. So this is your primary beam, okay, and this is the target angle. When you're talking about those electrons coming across from cathode to anode, you are talking about the number of electrons come across is just millions of billions. I'll probably illustrate this for you in a visual video because it'll make a lot more sense if I do it that way versus just trying to tell you the number on here. I will tell you the number, but if you were set at 1 mass on your control panel, the cathode would release 6.24 times 10 to the 15th, which is 6.24 million billion electrons. All right, one mass is pretty insignificant with what we use. But if you were set to one mass, you would release 6.24 million billion electrons. What does that look like if I wrote it out? It'd be 624 with 13 zeros behind it. So that's the potential number of X-ray photons you could have in the primary beam. Now, the reason that's significant is because we said that if you are creating X-rays, 99% of what you create is heat, only 1% of that is X-ray exposure, which sounds really insignificant, and it is. But if I said that I won in the lotto $6.24 million billion, and I was going to give you 1% of those winnings, I don't think anybody would turn me down, because that would be a significant amount of money. 1% of that, I believe, be 624 with 11 zeros behind it. So if you think about that in terms of money, that's a whole lot of money. So even though it's an inefficient process, for what we do, it's very effective. All right. Now, the last part of this lecture, the second part, we'll talk about the cathode and the rest of the chapter. But when we talk about the anode and the anode heel effect, basically, when the target angle becomes too small, what happens is that the beam area might not be big enough to fully expose a 14 by 17 image receptor at a 40-inch, what we call SID, or source to image receptor distance. All right, and because of that, what you also end up having happen is that the heel of the anode, meaning this portion right here, actually can absorb some of the radiation that you create, right? Because it has to pass through that in order to get out. But if you look on this side, there's nothing but air to interact with, correct? So when you have the anode heel, what it says is that when you create the radiation, some of the radiation is going to be absorbed in the heel of this anode, so that you end up with less on this side, more on this side. This happens to be the anode side, which is positive. This is the cathode side, which is negative. So you end up with more photons on the cathode side than you do on the anode side. And typically, I always tell you guys, we call it fat cat, meaning, why do I call it that? You typically put the thicker portion of the patient underneath the cathode side, because you have more photons exiting that side, which means you have more potential for this to have proper penetration on the cathode side. Okay, so you tend to put the thinner part under the anode and the thicker part under the cathode if you were trying to image. That used to be what we did. Now, pretty much with the addition of digital imaging, it is not as big a factor as it used to be. You typically still would want to place that area of the patient underneath the cathode, but if you didn't, because digital is so much more forgiving than film was, you probably wouldn't have that big of a deal if you didn't do that. But the whole point of it is that the heel in this anode is actually going to absorb some of the radiation. The cathode side, it is not going to absorb as much radiation, so that you end up with more intensity or more quantity of photons on the cathode side than you do on the actual anode side. All right, and that is called the anode heel effect. So it says that the angle causes the intensity, which is your quantity, which is the number of photons. It causes the number of photons of the X-ray beam to be less on the anode side, because some of the X-rays get absorbed in the heel. And that is called the anode heel effect. And that is on page 57. So far, everything we've talked about begins on page 53 and takes us up to page 57 with the anode heel effect. The second part of this will actually talk about the cathode. All right, we'll talk about the cathode, and then we will discuss some other aspects of this chapter. And notice that they do reference that the image tends to be lighter on the anode side versus the cathode side because of that loss of quantity of photons. So like I said, you typically want the thicker or fatter portion of the patient under the cathode side of the tube and the thinner portion of the patient under the anode side of the tube. Right. And that takes us to the end of Chapter 5, Part 1 lecture. Make sure you take notes and be sure to stay tuned for Part 2. Thank you so much.